So good evening, good afternoon, my dear friends. We'll continue the second session. Some of the friends are there getting a doubt in the question number 35 of chapter number 3. So I have given the solution here. Already explained during the when some of the friends are asking the query now. In the question, load intensity is given minus Wxx equal to df by dx. Substitute the load intensity. Load intensity is given W sin pi x by L. In the question is given as what now? Sin load intensity is given now. So in the question is given as load intensity as this is given in the question. So substitute that load intensity. Then first time integration, you are going to get a shear force equation C1, but we don't know the boundary condition for the shear force. Next, F equal to dm by dx. One more integration is going to get the Bendmeter equation C1x plus C2. Always at the simply support beam is given, a simply supported beam is given. Simply support beam always Bendmeter is 0 at the support, that is at x is equal to 0 and x is equal to L, Bendmeter is 0. Now if you can substitute this, now then you are getting the C1 and C2 are 0. Then the Bendmeter equation will be mxx w L square by pi square sin pi x by L. And the given condition is symmetric condition. Symmetric condition, always the Bendmeter is going to be maximum at the midspan. Always in simply supported beam, symmetric loading, Bendmeter is going to be maximum at the midspan. So it asks the maximum Bendmeter, then x is equal to L by 2, Bendmeter is m max. So put it L by 2. X is equal to L by 2, then you are going to get it W square L square by pi square. This term will become as a 1. So maximum Bendmeter is W L square upon pi square. So answer is what now? See the answer for this question now. So this is the answer some of the friends was asking now. So we are continuing with your Castigliano's theorem. 4 examples here discussed. One more example we are going to discuss, that the overhanging beam subjected to constant point load. So once again, this is the unsymmetric loading. Under unsymmetric loading, always Castiglione theorem is better now. Now here, Castiglione theorem is better for the what now? Calculation of the deflection at B. Calculation of the deflection at B. Sorry, deflection at A. At B 0. At the point of application of load. Now first find out the reactions. You have to, which reaction required? RC is required or RB is required? RC is required. So directly bendment is what now? W into X. Yes, strain energy of AB and BC are different. Strain energy of AB and BC are different because of what now? Limits are different and reactions also different. So you have to calculate both the strain energy of AB and BC. So now you need the RB is required or RC is required. RC is required. So you want to find out the bendment, you are taking the right side. Therefore RC is required. RB the optional. RB is not required now. So how to get the RC now? Take the sum of the moments about B. Take the sum of the moments about B. RB the optional. I am interested only in RC. So directly take the sum of the moments about B is equal to 0. Sum of the moments at B is equal to 0. How much is this now? Minus W into L by 4. And this is clockwise. It's also anti-clockwise. So RC into L. So from this one RC will be minus W by 4. What's the meaning of this now? Assumed direction is incorrect. So RC will be downward. RC is downward. So then you can write down the strain energy. By chance if you ask the RB, then you can use the sigma V is equal to 0. Here you cannot use any shortcut method. No, you have to go for a general method only. If you ask RC, directly take the sum of the moments about B. Suppose you are also interested in B, RB, then you can go for the sigma V is equal to 0. So change this direction now. Then by using sigma V is equal to 0, RB will be strain energy of AB plus strain energy of BC. AB limits are 0 to L by 4. What the bendment equation now? So complete the integration now. Then deflection at A. Deflection at A. Five WL cube upon 192 EI. 5 WL cube upon 192 EI. Here you cannot use the shortcut method. Shortcut method is valid only for simply supported beam. Clearly mentioned, shortcut method is not valid for the overhanging beams. The shortcut method valid only for simply supported beams. Now the same question is given in the workbook. The same question given in the workbook. This replaced by flexible support. Replace the flexible support by a spring. This question can also be done with the other methods now. But this question obviously you have to go for a strain energy. This type of same question you have studied when you are studying the strain energy impact loading now. Impact loading you have discussed. Simply support beam replaced by flexible supports now. But here only one flexible support is given. So whenever a beam is supported by flexible supports, To find out the deflection, always strain energy is required now. That the Castiglione theorem is required. This question can also be done with the Michaelis method, any other method now. But here, whenever a flexible support is given, you have to go for the Michaelis method. Is no other method is valid. You have to go for the only Castiglione theorem is required. So what change you have to make it now? This is about whatever you got the strain energy of the beam. Strain energy of the supports are 0. These are the rigid support. Here what you have to do it now? You have to add the strain energy of the spring. Strain energy of the beam will remain same. We have done the same question in the impact loading question now. So add the strain energy of the spring. Then you differentiate it with respect to now. When I am going to replace the flexible rigid support by flexible supports, when I replace the rigid support by flexible support, what happens now? Reaction will remain same. SFD, BMD will change. Only deflections are going to be changes now. Deflection will increase. And what the reaction, you got it here now. Is the reaction for provided by the spring. But what about the action of the beam now? Will be axial load. So the action of the beam will become for the spring is a tensile load. Action of the beam for the spring is become as a tensile load. So what change you have to make it now? SFD, BMD for the beam is same. Reactions are same. Only deflections are changes because of the flexible support. So more deflection will get it. More deflection will get it. So how to get this now? Add the strain energy. Strain energy of AB plus strain energy of BC plus strain energy of the spring. How to find out the strain energy of the spring you have studied now? Half W into deflection. Strain of work done method can be used it now. Strain energy of the beam plus strain energy of the spring. Strain energy of the beam already got. This is strain energy of the beam. How much you got the strain energy of the beam now? 5W square L cube by 384 EI. How to find out this now? Strain energy of the spring. Half load into deflection. So this will become as what now? You can use the work done concept. Half P into elongation. What the elongation now? P by K. So can use the strain energy equal to P square by 2K. So whenever the spring is given, if you know the stiffness, you can use the work done concept P square by 2K. So what this value got it now? 5 W square L cube upon 384 EI. What the load acting on this now? W by 4. And stiffness is so it will be 1 by 48. Those who have attended the impact loading now, same thing you have studied now. Flexible supports are required under impact loading that you have used now. Suppose this also spring is given now, then you have to add the strain energy of the one more spring. Now you can see now when both the rigid supports are there for the deflection of 5 WL³ by 192A. Now if I am going to replace the one rigid support by flexible support, so deflection is what now? 13 WL³ by 192 EI. So for this question, obviously what now? Castiglione theorem is compulsory. This question is directly from the workbook question only. Only numericals are changed now. This was a question I kept in the workbook. Mr. Swaraj Pandey also mentioned about now. This I kept it only one of the student is appeared for a bark interview now. Is a shared me this question now. Sir, you are in the class, you are discussed how to draw the SFD BMD when a rigid supports are there. But when a flexible supports are there, how to do it now? Then afterwards next year this question was introduced in the workbook now. And you have studied the same thing even in the impact loading now. The cantilever beam subjected to point load at the free end. It is what the deflection is WLQ by 3 EI. But that formula is valid when EI is a constant. But here EI is not constant. So here most of the classes I used to do with a moment error method. But here you can use directly the Castiglione theorem. You can find out the strain energy of AB and BC, add it, then differentiate it with respect to W. In both the case, what now? Synergy of AB plus BC. What is the reaction now? And what the moment reaction now? So what the bendment here now? W into X. Limits are 0 to L. What the bendment equation of BC? Minus WX. What about AB? AB also equation is same. Better take the left side or right side now. Right side is better now. But limits are changes now. Limits are what now? AB. For this case, what the limits now? 0 to L. 0 to L. For this one, what the here better to take the left side or right side is better now. Right side is better. Right side only one moment is, but left side what now? One couple is there, one moment is there. Once again you take the right side. If you take the right side, so once again what the Benjamin equation now? W into x only. But limits are what now? Limits are what now? What this case limits are what now? L to 2L will be there now. L to 2L. So now you can find out the strain at G now. What the flexural rigidity? 2 EI. Second case, what the limits now? 0 L to 2L minus WX. But what the flexural rigidity? 2 EI. So you can complete this integration now. Then you can differentiate with respect to W, you will get the deflection. So it will be six EI, and this is W square by 4 EI So what this value you are getting now? 12 whole cube, that is what the 8L cube minus 7L cube, you are going to get it now. So if I can take out the W square L cube by EI is common. One by 6 plus 7 by 12. Then deflection at C. So complete this portion now. Anybody about the final constant? Can you give it now quick? Nine by 12. This is 9 by 12, but overall what? This one is what now? 9 by 6 you will get it, I hope. Same, if a concentrated moment is given, then you can find out the slope can be calculated now. If a constant moment is given, you can find out the slope. This question in the gate paper, it is also once again in the workbook question. Or the answer 3 by 4. Okay, 3 by 2. So it will be 9 by 6 means 3 by 2 only. And one of the paper they asked what now? What is the stiffness is asked now? What the stiffness mean? What the answer here now? For this question, what is the stiffness means? And what is the deflection is asked now? A frame. This is nothing but about a frame. So once again for this question, Castiglione theorem is compulsory. 3 by 4 or 3 by 2 final. This will be a 3 by 4. Final deflection will be 3 by 2. Now here what you have to do it once again now. At the synergy of AB and BC. But for this member, it is a, how many loads are there now? Shear force and bendment. Is a TSL. For this member, the eccentric axial loading. So here how many synergies are there now? Axial load as well as bendiment. For this member is about now TSL. So you are getting a shear force and bendiment. But here is the eccentric axial load. For this member, the which type of load? Now, eccentric axial load. What the eccentricity? W. And for this member, the TSL. So once again, you have to calculate the strain energy of AB plus BC. AB member, we are considering only due to bendiment. In the question what now is clearly mentioned what here how many loads are going to be there, shear force and bendiment. Always the strain energy due to shear force neglected. But in this one, we are going to get an axial load. Every eccentric axial load equal to one axial load and one bendiment. Axial load and bendiment. But in the question clearly mentioned what now? Neglect the strain energy due to axial load. So if you neglect the strain energy due to axial load, the bendiment is a constant. It's a pure bending. M square L by 2 EI. So what the bendiment in AB portion? W into L. Once again, what the deflection at C? But this is by neglecting strain energy in AB due to axial load and strain energy in BC due to shear force. If I draw the Fibor diagrams, what will get it now? If I draw the Fibor diagram, it is just like a cantilever beam. Next, what about the AB member? So in this member, you are going to get a shear force that is neglected, always neglected. But in this member, axial load is also there. But that is clearly mentioned about now. Neglect the strain energy due to axial load. Refer the question in the workbook now. Clearly mention neglect the strain energy due to axial load. But strain energy due to shear force is not mentioned now. Strain energy due to shear force should be neglected. It is not mentioned in the question now. But one of the very old paper, in place of the fixed support, it is given as a hinge support. In place of the what? Now fixed support, hinge support is given. Hinge support, there is no moment reaction. Then who will balance this couple now? Horizontal reaction will be there. This is about now latest, maybe 5-6 years back, but one of the very old paper of the gate mechanical now. If you refer the previous old gate papers now, this is replaced by fixed support, replaced by hinge support. If you go for a hinge support, there is no moment reaction. This couple is balanced by this moment reaction here now. But if I am going to replace by fixed support by hinge support only horizontal and vertical reaction, no moment reaction. Now who will balance this couple? At that time horizontal reaction will be there. And because of that horizontal reaction, bend moment is going to be varies. Then once again here also you have to go for the integration. But in this member, what a pure bending. Bend moment is constant. Therefore, directly you use the m square L by 2EI. What the bend moment value? Now WL. And or directly can tell it now. Eccentric axial load bend moment equal to load into eccentricity. But here bend moment is varying. Then you have to go for the integration. You can do it now. But AB member is here optional. Bend moment is a constant. But here if I am going to replace by hinge support there is no moment reaction. So who will balance this couple now? To balance this couple, then you are going to get one horizontal reaction will be there. So, and due to this horizontal reaction, it will become as a constant load. Then bend moment will vary. Then in that case, once again you have to go for the integration. So that refer it what now? If I slightly change the support, a completely problem is going to be changes now. So when this supported by fixed support, it is a bend moment is a constant. But if I am going to replace by fixed support by hinge support, there is no moment reaction. Then who will balance this couple? Horizontal reaction. Here horizontal reaction 0. But if I am going to replace the fixed support by hinge support, no moment reaction. But horizontal reaction will be there. Why that horizontal reaction is required now? To balance this couple now. For all these questions, your Castiglione theorem is compulsory. And we'll study one more last question. This is in one paper, it is given like this now. Now roller support will permit the axial motion. They ask what is the axial motion at this support now. Roller support will permit the axial motion. Now for the axial motion. So once again this is going to be a frame. So for all the frame questions you have to do the Castiglione theorem. Now once again find out the strain energy of AB, BC, CD. Now for AB member, this is which type of load now? Constant and point load, then bend moment varies. For BC member, the eccentric axial load. Same question, only one more member is there now. For BC member, this which type of load now? Eccentric axial load. What the eccentricity? L by 2. And here once again strain energy of AB and CD are equal. Here you are going to get a reaction. So what the bend moment now? P into X. Limits are L by 2. Here also what the same. But for this member is the eccentric axial load. Every eccentric axial load equal to one axial load and one bending couple. So 2 times the strain energy of AB plus strain energy of BC. AB member, what the limits now? 0 to L by 2. P into X. BC member, pure bending. What the bend moment? M square L upon 2 EI of BC portion. Once again, which one is neglected now? Axial load is neglected. In this member, once again, the strain energy due to axial load is neglected. In these two members, strain energy due to shear force is neglected. What, Rishabh Yadav, are you attended my lectures or not? After coming to the subject, you are getting a doubt. What is the EATL? What should I answer, my dear friend? Don't behave like after listening entire Ramayana. What the relation between Rama and Lakshmana? Sir, I don't know, sir. You have attended all the lectures now. Almost 140, 150 hours lectures are completed now. And you are asking what the EATL. Please refer your notes now. What the EAL, eccentric axial load, eccentric axial tensile load. So many times you have studied now. Are you sleeping or what? For so many days now. You are asking what the EAL, what the EATL. Starting itself we have done it all this thing now. So once again this strain energy is what? By neglecting the strain energy due to shear force in AB and CD, as well as what now? Strain energy due to axial load in BC. Due to axial load in BC. I didn't ask what is the TSL, sir. Check properly, Mr. Abhyuday Sharma. X square integration. X square by 3 denominator is there now. And L by 2 whole cube. So you are going to get 24 or 8 you are getting now. This term you are telling, okay. This is 8. Second term is 8. Then this constant is going to be 4 into 2, 8. Okay. So it will be 3. So this constant will change. 4 by 24, that is 1 by 6. So slightly change here. What now? 8 will be there now. I taken as 2. 4 I taken. So it will be 1 by 6. Then this will be so this is one last question. It is also given in the workbook. Almost all the questions of the Castiglione theorem questions of the workbook I am doing in the class itself now. A quadrilateral ring is given. A quadrilateral ring. A tube is considered. Tube is hollow. A tube is going to be bent in the form of a quadrilateral ring. Sometimes it is bent in the form of a semicircular ring. Semicircular ring. One end is a fix and here load is applied. In the workbook it is given numerical data is given. I am doing in terms of EI. A tube means inner and outer diameter is given. But I am doing without numericals now. Now once again for this type of question we need the Castiglione theorem is compulsory. So what you have to do it now? So far you have taken the strain energy of the straight members now, but this is a curved member. Then what you have to do it? How we got the strain energy of a straight member? We have considered a small strip of length dx. We have considered a small strip having a length of dx. Then you have done the integration. Here also what you have to do it now? Consider a small elemental ring. Small elemental ring. Take a section. The length of this elemental ring is what now? Dx. Such that it will subtend an angle of and this will be at an angle of theta. Consider a small strip of length, arc length dx, such that it subtends an angle of d theta at the center, and this strip is at an angle of theta. So what the limit for theta now? 0 to pi by 2. 0 to pi by 2. Now what the strain energy of the strip now? Mxx whole square dx upon 2. But what the length of the strip now? What the arc length RD theta? So what the limit for theta here now? If a quad semicircular is given, limits are 0 to pi. Now what the bend moment at xx now? What the length of the small strip? RD theta. RD theta. But what the x value now? X value you write down in terms of theta. But x is equal to r sin theta. So mxx is equal to now you can do the integration 0 to pi by 2 mxx whole square dx upon 2 ei. Here ei is constant. That is minus dx equal to rd theta. Sin square theta is equal to 1 minus cos 2 theta by 2. Sin square theta is 1 minus cos 2 theta by 2 d theta. Do the integration. How to get the x value now? X is equal to r sin theta, y is equal to r cos theta. What is the final constant? Pi by 4 or pi by 2 here now? Deflection constant. Some students are writing dx means, sir, r cos theta d theta. Dx is not the differentiation of this, no. Dx is length, arc length. Sir, x is equal to r cos theta, then dx equal to r cos theta d theta. They are going to write down, no. Dx is this small length, arc length equal to what, no? L equal to r theta. So dx equal to r d theta. Most of students, they are going to get it out. Sir, x is equal to r sin theta means dx is r cos theta d theta. Dx is not the differentiation of this, dx is the length of this small strip, arc length equal to r theta, r into d theta. You have to find out the maximum bending moment. Then you can do the differentiation. Maximum bending moment, you can do it now. Already one of your friend is given also same doubt now. Sir Rajanshu, sir, x is equal to r sin theta, then dx equal to r cos theta d theta. That only I mentioned now. I not checked your doubt, my dear friend, but this type of doubt everybody is going to ask in all the batches now. So this complete the deflection of the beam chapter. Now with this one, you can complete all the workbook questions except one or two questions. For one or two questions, you need the moment era method. So that I am not discussing that moment era method. It may be 1-2 hours lecture will be recorded and uploaded now. But in place of that only, I done all the, now all the questions of the workbook, only two questions cannot be completed directly with the this now. For two questions, you need a moment era method is required. So remaining all the questions directly can complete. That's why I spend the sufficient time now. So overall what now? Castigliane's theorem should be used compulsory when now. I'm going to quickly revise the Castigliane's theorem. Castigliane's theorem is compulsory for all unsymmetric loading. Next, a frame is given, a curved member is given. A frame is given or a curved member is given. So to find out the slope and deflections, you can use it now. And this method becomes simple to find out the slope at a cross section where constant moment is applied. And it becomes simple for deflection at a cross section. It becomes simple for deflection at a cross section. Deflection at a cross section where constant point load is applied. And what is the drawback of this method now? It is not valid when the loads are acting at multiple cross section. When the loads are acting at multiple cross section is not valid. Next, it will not give the direction of the slope and direction of the bending moment. Check it, anybody, somebody is getting pi by 4 and somebody is getting pi by 8. Final constant, you check it now. Probably here you are going to get pi by 8. Then you are going to get pi by 4. Mr. Raghav, you may be incorrect now, check it. Anybody cross check it now? One of your friend Mr. Raghav is getting here pi by 8. I hope it should be pi by 4 only. Here you are going to get pi by 8, you are going to get it now. Is it pi by 4 or pi by 8? We check it now. Final now, deflection equation now. Should be used when loads are acting only at one cross section. Becomes simple to determine slope at a cross section where constant moment or bending coupled with acting. Becomes simple to determine deflection at a cross section where constant point load is acting. Should be used under unsymmetric loading, under flexible supports, beams with flexible supports, frames and curved members. What is the drawback means? Already studied now. It is not used when the loads are acting more than one cross section, as well as what now? It will not give the direction of the slope and direction of the deflection. This is correct only. Pi by 4 is correct. This is going to be pi by 8 will be there now. And variable EI also. Variable EI. All your equations are valid when EI is constant. When flexural ridge is varying, can also be used now. Should be used under unsymmetric loading, beam with flexible supports, frames, curved member, as well as what now? Variable flexural rigidity. Variable, we have taken one question on what? A stepped cantilever beam. Stepped cantilever beam. Now read on the next topic, that is the shear stress in the beams. Chapter number 5, one topic is bending, shear stress in the beams. Still some of the friends are getting pi by 2, pi by 8 they are getting now. Check it. Somebody is getting final answer in the previous question. That quadrilateral ring question. Somebody is getting pi by 2, pi by 8, pi by 4. I hope it should be pi by 4 is the correct answer now. But still somebody is getting pi by 8 as well as pi by 2. So this, we have completed the bending stress, we have completed. But one topic is pending in the chapter number 5, shear stress in the beam, that was not discussed because of by that time you are not completed the SFD BMD. Bending equation derived assuming the pure bending, bend with the constant shear force 0. But what you have studied now? Whenever a beam is loaded by transverse shear loads, that is constant point loads, constant moments UDL and UVL. Total beam never will be under pure bending. Total beam never will be under pure bending. But a part of a beam is a pure bending. Part of a beam is a pure bending. Part of a beam may be pure bending. Bending equation derived assuming the pure bending. So strictly speaking, bending equation valid only under pure bending. But most of the beams are loaded by transfer shear loads. Under transfer shear loads, always bendment is varies. Always bendment is varies. Whenever a bendment varies, shear force is not zero. Then you are called as what? Most of the what? Total beam is not under pure bending. But a part of a beam may be under pure bending. Now we are going to discuss how to find out the shear stress due to the shear force acting on the cross section. We have studied how to find out the bending stress due to the bendiment acting on the cross section. Now we are going to study how to find out the shear stress due to shear force acting on the cross section. Default which shear force you have to consider? Now, maximum shear force should be considered. Objective examination directly they are giving the maximum shear force. But in some of the gate and civil service paper, they are giving a beam and find out the maximum shear stress. Then what the student has to do it now? He has to draw the SFD. He should draw the SFD. Then from SFD, he should determine the maximum shear force. Maximum shear force. And if I, based upon last 30 years papers, if I see the entire questions now, out of the entire subject, this chapter the least priority. Till 2022, I am telling now. I don't know what is going to be happening in the 2023. Till 2022, out of all the papers now, last 25 or 30 year papers now, this chapter is having the least priority, especially mechanical papers now. Even when compared to remaining all the topics, even columns, thin pressure vessels, questions are more. But this is what now, if I see the last gate, almost 10 to 15 years paper, hardly one question is there. Only one question is there. I am telling only till 2022. My intention is not that what now you have to leave this chapter. When you are preparing, you should give the least priority for this now. The topics which are important for that one, you have to give the top priority. You need not, I'm not indicating, sir is mentioning the least priority means better. It is not a university examination can predict. Nobody can predict it. Clearly mentioned, conical bar under sulfate 2021, never there is a question is there. But suddenly there is a question in the 2021 is there now. Okay, everybody is getting pi by 4 good. Mayank Sharma, Phule Saket, Anurag, Raikwar, they are all getting pi by 4 only. Good. Let tau is the, let me write down the terminology and the equation now. This equation, what the derivation will take the more time. The derivation of the shear stress equation. Let tau is the shear stress developed at a fiber, developed We have studied how to find out the bending stress at a fiber. Bending stress at a fiber is going to be calculated by my by I or Ey by R or sigma B max into y by y max. Now we are going to discuss how to find out the shear stress. P A y bar upon I into B. Now this is one equation should be remembered. So now what is the terminology on this equation terminology? Tomorrow morning session I am going to complete the theories of failure, because I am informing right now, because once again at 5 o'clock, 5:30, mostly 5:30 we are going to close it. Some students are going to log off the systems. But tomorrow morning, 8 o'clock, we are going to start with the theories of failure. What is the very important topic for mechanical engineers? You should be thorough with this topic if you are going to be thorough with the completely principal stress and the Mohr circle. Mohr circle. And for that one, already summary table is uploaded for you. All of you, please go through the table, and bottom of the table some conclusions are given. With that one, you can complete once again all the workbook questions. You can complete it now. My suggestion is, please prepare your table once again on your own. If you are going to write down, then you are going to clear what you are writing, what is given now. So tomorrow once again I will not write down the table on the board. All the questions we are going to do it by using that summary table of theory of failure. That is very important now. When you are going for examination, if you can refer the table, your revision of the theories of failure is completed. And apart from the table, and tomorrow starting I am going to discuss some important conclusions, around 10 to 12 conclusions. The starting 12 conclusions as well as the tabular form which is uploaded, summary table. With this one, you can complete all the questions now. I complete the principal stress, but I not continued the theories of failure, because by that time we are not the strategy or not a discuss. For theories of failure, in it the strategy concept is required. There are two theories, total strain theory as well as distortion energy theory. Okay. Now I am going to write down the terminology. Already I written the tau. Tau is the shear stress developed at a fiber on the cross section of the beam. Next, what is the P? P the shear force acting on the cross section of beam. Shear force acting on the cross section of beam. Most of the question, objective question, directly they are giving the shear force. Especially ESC paper, no, engineering service paper. But gate paper, they are giving the beam is going to be given. Then you have to draw the SFD, and then you have to take the maximum shear force. So this is obtained from SFD. A, area of hatched portion, of cross section of beam which is above the neutral axis. Either not the total area, either what area of hatched portion of cross section of beam which is above the neutral axis. But shall I take it above or below? If it is going to write down above. If this fiber is above the neutral axis, fiber is above the neutral axis, then I have to take it above area. Sorry, this is above the fiber, not neutral axis, above the fiber where shear stress is to be determined. Where shear stress is to be determined. Now if this fiber is what I am taking above means I am assuming the fiber is above the neutral axis. By chance the fiber is considered below the neutral axis, then you take the below area. So here I am assuming that fiber is above the neutral axis, that's why you are taking above. If the by chance the fiber is below the neutral axis, then I have to take the below area to consider now. Next, y bar, distance of centroid of hatched portion from neutral axis of that cross section. So what this AY bar? First moment of area first moment of area of hatched portion, first moment of area of hatched portion neutral axis of that cross section. I already have studied now when you are studying the bending equation. What this I now? Moment of inertia. That is what a second moment of area of the entire cross section. This is for entire cross section, but this is for what now? Only the portion above that fiber, portion above the fiber. B. B the width of the cross section. Width of the cross section where shear stress is to be determined. Some of the friends are requesting for machine design, but mostly last year also so many prime batches was requested, but it is not my hand. That is, decision is going to be taken by Medici management, because they are going to have some. They will take care of what now. But I informed last year, I requested some of the batches are requesting, but they have not considered my request. So I'm not going to be sure whether I'm going to take it. Mostly 99% I may not handle. Another, my student, Mr. Padmesh sir, who has attended my lectures, is going to take your machine design. He is also best teacher. All the teachers of Medici are the best. So he's going to take the, but you will get the entire information from the Padmesh sir. Is going to be 90% whatever you are getting from Padmesh sir is going to be my class notes only. So you need not worry. You can easily follow the machine design will become easy once your this subject is going to be thorough now. Only few batches I am going to take it, only offline batches of the few centers like Hyderabad, Bhopal and the Pune center, where I am going to take the machine design. But most of the prime batches last year has not taken. Mr. Padmesh sir has taken. Mostly this year also he will take the, Padmesh sir will take your batches machine design now. Okay. So now I am going to explain this terminology. Now, from this equation, what you can mention it now. Out of this now, which parameters are constant for all the fibers? On a cross section, how many fibers are there? Na? Infinite fiber. Out of this 5 now, which parameters are vary from fiber to fiber? Load never will vary. Load is what? A constant. Load will vary from cross section to cross section. Load never will vary on a cross section. Always ALD, SFD, BMD, TMD means what now? They are representing how the load is varying from cross section to cross section. So load never will vary on a cross section. Means for all the fiber, load is constant. Therefore P is constant. And I is also constant. I is also for entire cross section. But which one will vary now? Area will vary. Y bar will vary. B will vary. For a given cross section, for a given cross section, P by I the constant. Hence, even when you have studied the bending equation also, what you have done it now? M by I equal to sigma B by Y, and sigma B equal to My by I. Sigma B equal to what you got it now? My by I. Then you have written sigma B proportional to Y, because for a given cross section, which one is the constant? Bendment is constant and I is constant. So now where the shear stress is maximum now? At which fiber shear stress maximum? Shear stress is maximum at a fiber where ratio of AY bar upon B is maximum. Shear stress is maximum at a fiber where the ratio of AY bar upon B is maximum. But bending stress, what you read now? M by I is constant. Then bending stress proportional to Y. So directly bending stress is depend upon only Y. So bending stress maximum where Y is maximum. Y is maximum at the extreme fiber. That's why bending stress always maximum at the extreme fibers, far away from the neutral axis. But the shear stress is what now? Depends upon three parameters, AY bar upon B. When B is constant, which cross section width is constant? For all the fiber, width is constant in which cross section? No. Square and rectangular. Square and rectangle, everywhere width is same. But triangular, circular, SD, fiber to fiber width is changes. So when width is constant means that is square and rectangle. So shear stress directly proportional to AY bar. So in square and rectangle, the shear stress maximum at a fiber where AY bar is maximum. That is, example is next. When AY bar is constant, shear stress inversely proportional to B. This is in case of what now? AY bar is constant at the junction of flange and web. Horizontal rectangle called as a flange, vertical rectangular web. So at the flange and web, junction of flange and web. This is at the junction of flange and web. At the junction of flange and web, AY bar is constant, then shear stress inversely proportional to B. Now this is about the fiber above the neutral axis. Now I want to find out the shear stress. F is the shear force acting on the cross section. F is the shear, or P is the shear force acting on the cross section. Suppose if this cross section at the mid span of a simply supported beam, if this is a cross section, this is what now? Cross section of a simply supported beam at mid span subjected to point load at the W. If this is a cross section of the simply supported beam midspan, which is subjected to constant point load at midspan. Then in that case, what is this P value now? At the midspan, what the shear force value now? A simply support beam subjected a point load of W at the midspan. I am considering a cross section at the midspan. Now what the shear force value now? W or W by 2? W by 2. Whenever a load is acting at the midspan, it is a distributed. So what the shear force value I have to take it now? W by 2. Next, if this is a cross section of a cantilever beam, it is a cross section of a cantilever beam at the fixed end. It is a cross section of a cantilever beam at the fixed end. And which is under UDL. Under UDL, what the shear force at the fixed end? Reaction. What the reaction value? Now WL. So in that case, the P value will be what? Now small w into L. Now the same, this is what now? Cross section at the midspan of a simply supported beam, which is subjected to UDL. At the midspan, shear force is maximum. Yesterday I completed now. For the shear force at the midspan of a simply supported beam under UDL? 0. At the midspan, what the shear force? No, 0. Shear force is going to be, two triangles are there. WL by 2, left side reaction, right side WL by 2. So what the SFD? Triangle, shear force 0, bending is the maximum now. So this P value is about now obtained from the SFD. So if this P is about now, if this is a cross section at the midspan of a simply support beam subjected to constant point load W at the midspan, then the P value is about a plus or minus W by 2. And if the cross section of a cantilever beam, it is a cross section of a cantilever beam at the fixed end under UDL. Then shear force at the fixed end means vertical reaction. What the vertical reaction under UDL? W into L. So this P value is obtained from the SFD. That only I written now. Now I want to find out the shear stress now. How to find out the bending stress now? Bending stress perpendicular cross section. This is what now? If it is about a hogging, here bending stress at tensile. So what? How to find out the bending stress here now? How many ways to find out the bending stress at a fiber? My by I or My by I or Ey by R or sigma Bmax into Y by Ymax. Now I want to find out the shear stress at this fiber, at all these points. At all these black color points, the shear stress is going to be given by this formula. How the shear stress will act now? Parallel to cross section like this now. Parallel to cross section. Therefore tau, if it is the X phase, if it is the X phase and this is the Y direction, then this will become the tau XY. Tau XY. Suppose the beam is subjected to HTSL, is a VTSL. Suppose the beam is subjected to HTSL, horizontal transfer shear load. When a shear force like this, then shear stress like this, now then this will become as about tau XZ. This is a Y axis, this is a Z axis. Then this will be about a tau XY. This will be tau XZ. On X phase, how many shear stress you have studied now? Tau XY and tau XZ. So in case of VTSL, this will be about a tau XY. In HTSL, the tau XZ will be there now. So this shear stress is going to be calculated with this now. So P the shear force that obtained from SFD. Next, what is the A? A is not the total area. A is not the area of the cross. What the area of this entire cross section? B into D. But what the A? A the area of the hatched portion, which is above the fiber. Now this fiber is above the neutral axis or below the neutral axis? Above. So I have to take it above area. This A. Suppose somebody is going to consider a fiber below, then I have to take it below area. Suppose somebody consider I want to find out some shear stress somewhere here now. I want to find out the shear stress at this point. Now these points are what now? On a fiber, this below the neutral axis or above? Below. Below means I have to take the below area. A dash. Now you can see it now what the A. Area of the hatched portion of cross section of the beam which is above the fiber, where shear stress is to be determined. But I written above, why now? Here I written above, assuming fiber is above neutral axis. Assuming that fiber is above the neutral axis. So by chance the fiber is below the neutral axis, I have to take it below area. Below area, that is A dash, you have to consider. Next, what the Y bar now? Distance of the, what the shape of this now? Rectangle. Centroid will be here now. This is Y bar. Y bar should be measured from where? No, neutral axis. What the Y bar you are written now? Distance of centroid of hatched portion from neutral axis of that cross section. Now this is a centroid. Now you can tell it now. This A and A dash are equal or unequal? Unequal. Why now? The fiber are different distance. This fiber is at what distance now? Now Y1 is greater than Y. Mean what the meaning now? As you are going away from the neutral axis, what happens now? Y will increase. As you are going away from the what now? Neutral axis, Y will increase. As the Y increases, what happens now? Area will decrease or increase now. Y1 is greater than Y. Y1 is greater than Y. But what about the A1? Less than A. A1 is less than A. But Y1 bar is greater than Y1 bar is greater than Y bar. Mean what the meaning now? Fiber to fiber, which one will change now? Fiber to fiber, what happens now? Area will change. As they are going away from the neutral axis, what happens now? Area will decrease or increase? Area will decrease. Y bar will increase. Area will decrease. Y bar will increase. Now this fiber is far away from this when compared to this fiber. This black color fiber, this fiber is far away because of what now? Y1 is greater than Y. Means as you are going away from the neutral axis, Y increases. As the Y increases, what happens now? Area will decrease. When area decreases, Y bar is going to be increased. Next, this area into Y bar is called about a moment of a area. Force into perpendicular is a moment of a force. This A into Y bar is called the first moment of area. What only written now? First moment of area of the hatched portion about the neutral axis. But what about this now? What the I? It's the for entire cross section. I is for the entire cross section. For entire cross section, what the moment of inertia? BDQ by 12. I should be for the entire cross section. But AY bar should be for this hatched portion. So which one is varies and which one the constant? This is a constant. This is for entire cross section. BDQ by 12. But fiber to fiber, which one will change now? AY bar will change. And next, what the B? B is not the width of the cross section. What the B now? Width of the cross section where shear stress is to be determined. This width I have to consider now. This width you have to consider. This width should be considered now. But here everywhere the width is same. But in which cross section width is same? Square and rectangle, square and rectangle. But if you go for a triangle, what happens now? If you go for a triangle, width will change now. If you go for a triangle, fiber to fiber width will change. B is not the width of the cross section. B is the what now? Width of the cross section where shear stress is to be determined. In triangular cross section, B is about a width at the bottom. That is not the width where you are calculating the stress. So if I am calculating triangular cross section, I am finding out the stress here now. I want to find out the stress here now. then this width I have to take it, no, not this width, no, this width at the bottom. So fiber to fiber, which one will change now? Fiber to fiber area will change, y bar will change, and width is also change. And which one is the constant? P is constant, I is constant. Load never will vary on a cross section. And I also will never will vary. I is what for entire cross section. Section modulus, area, polar mint of, this is the entire cross section. That is what now? Geometrical properties for a cross section are constant. So these two are constant. So shear stress directly proportional to AY bar upon B. So in this cross section where the shear stress maximum now, here fiber to fiber, which one will change now? A will change, Y bar will change, B will change. So when I am going to the neutral axis to, here when I am going to the neutral axis to extreme fiber, what happens now? When I am going to the neutral axis to extreme fiber, area will decrease, Y bar will increase, but width is also decrease. In this case, when I am going to the neutral axis to extreme fiber, area will decrease, Y bar will increase, width will decrease. A will decrease, Y bar increase, width will decrease. So directly we cannot tell it what where the shear stress maximum. Then what's your aim now? Always you are into the maximum shear stress. Then we don't know where the shear stress maximum. Then what you have to do it now? So what the aim of this chapter now? We want the maximum shear stress, but we don't know where the shear stress maximum. Fiber to fiber, what happens now? When I'm going like this now, area is decreasing, Y bar is increasing, and width is what? Decreasing. So where you cannot directly tell where the shear stress maximum. Then what you have to do it now? Take a arbitrary fiber. You take a arbitrary fiber. Then write down this AY bar by B. At that fiber, write down the AY bar upon B. Whenever you want to get a maximum value, what you have to do it now? Differentiate and equate to 0. So if you can differentiate this term with differentiate and with respect to y and equate to 0, then you will get it what where the shear stress maximum. So what the aim of this topic now? We have to derive a generalized equation for the shear stress at a fiber. Once you know the shear stress at a fiber, if you can differentiate and equate to 0, you can find out the where the shear stress is maximum. So you have to understand this term. If this terminology is clear, remaining is what was simple now. Now I am going to do what? If somebody will ask now, what you have studied in the shear stress in the beam chapter, what the answer now? Sir, we have derived the generalized equation for a shear stress. We have derived a generalized equation for shear stress at a fiber. Generalized equation for shear stress at a fiber. Why you have derived that equation? What the answer now? Sir, shear stress what now? Function of 3 parameter A, Y bar upon B. So we don't know where the shear stress maximum. So what the advantage of the generalized equation? If we can differentiate and equate it to 0, then we will get the maximum shear stress location. I am doing for one cross section, remaining all you have to do the same line now. generalized equation for generalized equation for generalized equation for shear stress at a fiber on now I'm drawing the rectangular cross section at the middle. I'm leaving the space on left side and right side. So you should also draw the rectangular cross section at the middle of the notebook. Leave the space on the left side and right side. Why the space is required now? Left side you are going to draw the bending stress. Already you have studied the bending stress variation. Now you have to make a comparison between bending and shear stress. So far you have made the comparison between axial and bending stress, and bending and torsional shear stress, and axial and torsional shear stress. Now only left out with what now? Bending and torsional shear stress in the beam. So always under simple bending on the cross section both shear force and bendment are there. Now you have to make a comparison between bending and shear stresses. So for that one we are going to draw the left side bending stress, right side shear stress. Then we are going to make a comparison. You are going to make it now. So this is a side view. Cross section beams are horizontal. Cross section can be seen in the side view. So this figure is about now. How many cross sections you are going to get now? So many shaped. I am taking a rectangular cross section. I have taken now. Cross section of beam. Or we are calling it the X face. X face. For the meaning of X face now. Polar axis, X axis, polar axis, X axis. Is a neutral axis. This you are considering as about the ZZ. HCA taken as a ZZ. This is VCA. Means we are assuming a vertical bending or horizontal bending. Neutral axis coincide with HCA under vertical bending, and beams are always unsubjected to vertical bending. This is YY. This will be centroid, or what you can call it now, X. So this axis, X axis, cross section are taken X. On X face, how many stress are there now? Sigma X, tau XY and tau XZ. What about this stress now? Sigma X. Which stress will be in the direction of the polar axis? Axial and bending. Axial and bending are perpendicular to the cross section. And this will be what now? Tau XY, tau XZ, tau XY, tau XZ, and this will be sigma X. Now consider a fiber. What this distance now? D by 2 minus y. This dimension is B. B. What are all these points now? What are these dots now? Points on the cross section. Points on the cross section, that is on this fiber. What the bending stress are all this thing now? Suppose the hogging. Hogging means here what now? Hogging means bending stress tensile or compressive. Tensile means like this now. So it will become as sigma x. How to find out this now? My by I or Ey by R or sigma B max into y by y max. So you already studied. Now you have to find out the shear stress. So how to find out the shear stress at all these points? What you have studied, bending stress will not vary on a fiber. For all the points, bending stress is same. Bending stress will vary from fiber to fiber linearly. Bending stress 0 at the neutral axis. When you are going away from the neutral axis, bending stress will increase because of what? A bending stress is equal to My by I. For all the fiber, which one is same? Bendment is same. Load will not vary. I is constant. For fiber to fiber, which one will vary? Y. So here y is 0, bending stress 0. Here y is maximum, bending stress maximum. So bending stress will vary linearly from fiber to fiber. But on a fiber, the constant. For all the points, bending stress is a constant. Similarly, once again, shear stress at all the points is a constant. But which stress will vary? No? Torsional shear stress will vary. When you are studying the torsional shear stress vary on a fiber. No? But bending stress constant, direct shear stress a constant. Now how to find out what the first step we have to do it now? This fiber is above the neutral axis or below? Above. Then I have to take it above area. If the fiber is below, below area is to be considered now. So what is the shape of this hatchet portion? What is the shape of this hatchet portion? Rectangular. So what is this area? Area is what now? B into D by 2 minus y. So if I want to find out the shear stress here now at the neutral axis itself. If I want to find out the shear stress at the neutral axis, what the area? B into D by 2. The total area consider now. When I am considering here now, I have to take it above area. So what is this area now? B into D by 2. So fiber to fiber, which one will vary now? Area will change. Just now you have studied now. When I am going from the neutral axis to extreme fiber, area will decrease. Area. A is not the total area. A is the area of the hatchet portion. Next, what is the expression for A? B into, what is this distance B? And D by 2 minus y. Sorry. D by 2 minus y. What is the next step now? Locate the centroid. For rectangle, you will get the centroid. Y bar. Y bar. Next. This is about the shear force. Beams are mostly loaded with a what now? Beams are loaded with a VTSL. I'm assuming the P the shear force. How to get a shear force now? Algebraic sum of the constant point load either on the left side or right side. Just now already studied. If this is a cross section at the midspan of the simply supported beam under constant point load means P is W by 2. If it is a cross section of a cantilever beam at the fixed end. Cross section of a cantilever beam fixed end under UDL. So what is this P value? No, W into L. And if the cross section of a cantilever beam, if it is the cross section of a cantilever beam under UVL having a intensity of W at the fixed end, free end, is a cross section of a cantilever beam at the fixed end which is loaded by a UVL having a intensity of W at the free end. So what is the shear force value now? shear force at the support equal to vertical reaction. Cantilever beam, what the vertical reaction? WL square by 3. WL by 3 will be there, no, WL by 3. Next, what the I? I for the entire cross section. What the I for the entire cross section? BD cube by 12. Then what the width? This width I have to take it now. What this width now? This width is what a B. So leave the space on the right side for shear stress variation. Left side for bending stress, right side for shear stress. So P the shear force acting on this cross section. Next, what the A? What the area value now? B into what the Y bar value now? Y plus, for rectangle you will get a centroid exactly at the middle. So what the Y bar value now? Half D by 2 plus Y. Next, what is required now? B. Everywhere the width is same. Now substitute this value. What about moment of inertia? Moment of inertia for entire cross section. B d cube by 12. B d cube by 12. Now substitute all the values. By substituting in shear stress equation. What is the shear stress equation written now? P A y bar upon I into B. What the A? What the Y bar? A Y bar upon what the moment of inertia? B d cube by 12. And B is B itself. So which term will get cancelled out now? So what is this equation now? 6P by BD cube. Now this is a generalized equation. This is equation valid for any cross section. Now this is valid for rectangular cross section. This is for every cross section. Now this is for rectangular cross section. So like this cross section to cross section, you have to derive this now. So cross section to cross section, which one will change now? Area will change, moment of inertia will change, B will changes. What the next step now? Is a generalized equation for shear stress at a fiber. So what the advantage of this equation now? Now we can find out the shear stress at any fiber can be calculated on a rectangular cross section. Is a generalized equation for shear stress on a rectangular cross section. This is what now? Generalized equation for shear stress for any cross section. Like that for cross section to cross section, the equation will change, that you have to derive it. But my aim is to find out the what now? Shear stress at every fiber or maximum is required. To get a maximum, what you have to do it now? Differentiate it. by differentiating second equation now. To determine maximum shear stress location. To determine maximum shear stress location. So shear y equal to 0. What is the differentiation of this? Now this is 0. 2y equal to 0 means y is 0. So shear stress maximum at the neutral axis. But bending stress 0 at the neutral axis. But shear stress I am getting maximum at the neutral axis. Now can you find out the maximum shear stress now? Substitute y is equal to 0. If you can substitute y is equal to 0. Now this is the maximum shear stress for on a rectangular cross section. Like this, cross section to cross section maximum shear stress will vary. But how to easily remember this equation? What the B into D area, what the P by A average shear stress. Generally P by A is represent the average stress. So what this P by A is called now when you are studying the what now? Direct shear stress here now when you are studying the stress definition. Sigma is equal to limit delta A tends to 0 delta Fn upon delta A. When shear normal stress uniformly distributed, what you read now? Sigma equal to P by A. Similarly, what the shear stress equation is written now? Limit delta A tends to 0 delta Fs upon delta A. So when the shear stress are uniformly distributed, tau d is equal to P by A. So this term is called as what now? Area. And what about this overall term is called now? This overall term is called as what? A P by A is representing average shear stress. So what is the maximum shear stress now? So this is easy to remember it now. Now cross section to cross section, this constant will change. If we go for a circular, this constant is a 4 by 3. This constant is a 4 by 3 for circular. Means in rectangular cross section, which one you can easily find out average shear stress P by A. For every cross section area is known. If you go for rectangular, area is B into D. Circular A square. Circular what? Pi D square by 4. Square A square. Triangular BH by 2. For every cross section you know the area. So which one you can remember average shear stress directly can get it now. Only this constant will change. So in case of rectangular, what this constant 3 by 2. So in rectangular cross section the maximum shear stress is 50% more than average shear stress. 50% more than average shear stress. But if you go for a circular, this is going to be 4 by 3. What the 4 by 3? 1.33. It means in circular cross section the maximum shear stress 33% more than average shear stress. If you go for SD, this constant is a 9 by 8. What the 9 by 8? 1.125. Means in SD, square cross section with diagonal and vertical and horizontal, maximum shear stress how much percentage more now? 12.5%. So now I'm going to modify this equation. This is for rectangular. This is for rectangular. This is valid for rectangular. Now this is valid for any cross section. Only now k value should be remembered. Circular k equal to 4 by 3. If you remember the k value directly can give it now. Almost 4 or 5 questions directly based upon the workbook engineering services based upon this now. Triangular, this count 3 by 2. This 3 by 2 is valid for triangular, rectangular and square. For rectangular, triangular and square, the constant is 3 by 2. SD 9 by 8. Only now area is already known. Can you give the directly tau max equation for circular? What the tau max equation? What the tau average for circular? P by A, 4p by pi d square into 4 by 3, 16p by 3 pi d square. If you go for SD, what this value in a 9 by 8? What about this value in a P by A? P by A square. So 9 by 8 into P by A square. If you go for a triangular, is a generally standard question. A circular and triangular will be asked now. Triangular, what about this value? Now area is BH by 2. So this is 2P by BH. And constant is 3 by 2. 3 by 2 into 2P by BH. 3P by BH. And remember what? Now, these constants should be used if clearly mentioned in the beam. But total machine design, the constant should be taken as one only. Most of the machine components, circular or non-circular, bolt is subjected to shear failure, rivets are subjected to shear failure, welded joints are subjected to shear failure. Most of the machine components are going to be circular. Then everybody is going to take the 4 by 3. You take the total machine design, the K value should be 1. In the design of the machine component, the design of bolted, welded, riveted, every entire machine design, we are going for average shear stress. Means I am taking a K equal to 1 means I am assuming the maximum shear stress and average shear stress are same. So total machine design, we are considering only average shear. This assumption is made. Why I am particularly mentioning now? In one of the gate paper that was prepared by ISC Bangalore, there's a numerical answer type question is given now. One of the I taken for that batch, strength of material, machine design is handled by other teacher. I given the 4 by 3. I thought that what a machine design teacher is going to discuss now. But the numerical answer type, the question is given as what the maximum shear stress on a bolt is given. Maximum shear stress on bolt. And what that student talent based student is done it now. He has taken what a bolt is about now, circular. He has taken 16p by pi d 3 pi d square. Sir, bolt is a circular, average shear stress 4b pi d square, K equal to 4 by 3. Therefore, he has taken 16p by 3 pi d square. Shear force is given now. But in the numerical answer type, he has given the answer by considering 16p by 3 pi d square. But when the ISC Bangalore is released the key, first they are going to release the key. If any deviations are, we can challenge that answers now. And that student from the talent batch, sir, ISC Bangalore is given the incorrect answer, sir. They have given the answer by considering 4p by pi d square, sir. Average shear stress is considered. But circular cross section, sir, you have to take the 4 by 3. You have to go for answer 16p by 3 pi d square. I clearly mentioned. In the beams means you have to go for 4 by 3. Machine design, you have to consider K. I not mention at that time because that will be taken care by machine design teacher now. What the student is done it now? I am clearly mentioned, don't challenge that question. If you challenge, ISC Bangalore will not. Why they will not consider, sir? You have to consider 16p by 3 pi d square. I clearly mentioned, Don't challenge it unnecessary that 500 or 1000 rupees you are going to lose it. Still, is this to argue, sir? You have mentioned 16p by 3 pi d square. That only I have to take it, sir. I mentioned this is what the beams. But machine design, clear assumption is there. You refer the any machine design. All the textbook, the clear assumption is what now? Average shear stress is considered. Sir, then how design is safe? That for factor of safety is considered now. Factor of safety is considered. In the all the machine design textbook, clear assumption is there. Strength of material study the assumption. Similarly, machine design textbook, clear assumption is what now? Whenever a shear stress is there, direct shear stress, average shear stress is considered. Therefore, they are going to consider P by A. But the student is what? Not bothered about that assumptions. And the teacher may not given that assumption now. But still, I mentioned yes challenge. But IIT Bangalore is not considered that now. So don't apply the one subject concept in other subjects now. Suppose by chance before this one metal forming is completed. Sir, engine mechanics, sir, my metal forming teacher is mentioned, you have to consider the engineering stress and engineering strain in the strength of material. Metal forming, you have to consider true stress and true strain, sir. In our subject, there is no engineering stress and no true stress. Both are same. Elastic region is both are same. But in plastic region, both are different. So don't try to apply the one subject concept in other subject concept. So that's why next time onwards, every batch I'm telling now. Even though whether I'm going to take the machine design or not. If clearly mentioned in the beam, use this constant. What you have written the title now? Shear stress in the beams. If machine component means K equal to 1 only, you have to consider now. Now, from this equation, what the conclusion you can make it from this equation? Tau is a function of y square. So what the difference between bending and shear stress in the beam? Bending stress is a function of y, proportional to y. But this is a function of y square. Means it will vary parabolically. So shear stress in a beam will vary parabolically. But shear stress in a beam varies linearly. What the next variation now? As you are going away from the neutral axis, bending stress will increase or decrease now. As you are going away from the neutral axis, y will increase, bending stress will increase. That's why bending stress maximum at the extreme fiber. But here, as you are going away from the neutral axis, y will increase. But the minus y square is there now. So shear stress will decrease or increase now. As you are going away from the neutral axis, shear stress will decrease, but bending stress will increase. Next, at the extreme fiber, bending stress is what a maximum. But extreme fiber, what the y value now? At the extreme top and bottom, what the y value? D by 2. Shear stress 0. So what the third difference now? At extreme fiber, only bending stress is there. Bending stress maximum, shear stress 0. That's why always at extreme fiber uniaxial state of stress. Is it a simple bending or a pure bending? If it is a simple bending or a pure bending, always extreme fiber only bending stress is there. Shear stress is 0. Extreme fiber, what the y value? No, D by 2. So always extreme fiber only bending stress. That bending stress is going to be maximum. So uniaxial state of stress is there. Uniaxial state of stress is there. Next, at the neutral axis, bending stress is going to be 0 because y is 0. But at the neutral axis, what the bending y value now? At the neutral axis, y is 0. Therefore, it is the maximum. So what the four differences are going to be there now? First one is what? A bending stress perpendicular to cross section. Perpendicular to cross section like this now. So it means it will be about now sigma x. But shear stress parallel. Then it is going to be tau xy as per this now. Bending stress perpendicular cross section, it will be in which direction? A polar axis. shear stress parallel to cross section. It will be in which direction? No, VCA direction. Here VTS, therefore the VCA. Which one is the VCA Y? So it is the tau XY. Next, bending stress varies linearly. Shear stress varies parabolically. Next, as you are going away from the extreme fiber, bending stress will increase. Shear stress will decrease. Next, at extreme fiber, bending stress is maximum. Shear stress is 0. Always, hence always extreme fiber. It is a pure bending or a simple bending. Always extreme fiber, only bending stress, uniaxial state of stress. Directly can use the strength criterion, can be used it now. Next, at the neutral axis, bending stress 0, but the shear stress is going to be maximum, will be there here now. But every time is not maximum, but in this case the maximum. But overall is a non-zero. At the neutral axis, shear stress is non-zero. But most of the case become maximum, but 100% always not maximum now. At the neutral axis, bending stress 0, but shear stress is non-zero, but becomes maximum in case of rectangular, square, circular, I section. But if you go for a triangular and SD, it is not maximum at the neutral axis. So these are the differences going to be there, bending and shear stress. So here, which type of stress are there? No, only bending stress. Only bending stress means only sigma x, uniaxial state of stress. But here, bending stress is there, sigma x, and tau xy is there, means a biaxial state of stress. Means you have to calculate the principal stress. What the state of stress inner fiber? No? Bending stress sigma x, tau xy, and tau yx. So on this is a cross section. This is a cross section. So this is going to be sigma x, and this is a tau xy. This is a combined stress. So if you ask the principal stresses here now, you have to calculate it now. And here only shear stress is there. Only shear stress. Mean pure shear state of stress. Pure shear stress. Therefore, how many state of stress are going to be there now? Under simple bending, that is when shear force and bendment both are acting. But pure bending, every time you are using uniaxial state. Pure bending means always shear force 0. Pure bending means on cross section shear force 0. When shear force 0, shear stress 0. Means at every fiber you are getting a uniaxial state of stress. But simple bending means what? Both. Simple bending, both shear force and bendment are there. Then how many state of stress are there? No, 3 state of stresses. What are they? No, extreme fiber uniaxial state of stress, inner fiber combined stress, that is sigma x and tau xy both will be there, and neutral axis you are going to get a pure shear state of stress. Tau xy and tau yx is going to be there now. Tau xy and tau yx is going to be there now. So this comparison very important now. From this only you are going to, in the principal stress chapter 1 question is there. They ask what now? Find out the principal stresses here now. So what the sigma x value now? Bending stress. And tau xy means tau s. How to find out the shear stress inner fiber? By using the equation. By using the equation you have to find out the shear stress. You know the tau xy, you know the sigma x, then you can find out the principal stress. But what about the bending stress proportional to y? As y increases, bending stress will increase. At extreme fiber, bending stress maximum. At neutral axis, bending stress 0. Now can you draw the variation here now? So what is this figure representing now? Shear stress variation for rectangular cross section over the depth of the beam. But what is the drawback of this figure now? This will give only variation and magnitude, but will not give the direction. Here we cannot identify the tau x for tau yx. So this figure will give only type of variation, means fiber to fiber it will varying parabolically, and you are getting a magnitude. It is going to give the magnitude as well as what now? Variation, but will not give the direction. Where you can see the direction here now? Shear stress parallel to cross section. So here shear force acting downward. At all these points shear stress same. What the value now? 6p by bd cube into d by 2 square minus y square. For all these points y is same or different? Now y is same. So for all the points stress is same. So how this will be there now? Upward direction. Because shear force downward. So this will become a tau xy. Parallel to which phase now? X phase. Y direction. So this will become as what now? Tau. Suppose it is a hogging. Hogging means what? A bending stress is going to be tensile. Mean bending stress perpendicular. Then this will become as a dot or across now. If it is a hogging, bending stress is a dot. Means this is a sigma x. So at this point, how many stress are there? Now sigma x is there as well as what now? Tau xy is there. So how many independent components? 3 will be there. Biaxial, how many independent components? 3. Sigma x, sigma y, tau xy. But here how many independent components? Only 2. Sigma x as well as what now? Tau xy. Sigma y 0. So this is what now? Sigma b, which is equal to sigma x. Now if I taken one more fiber here now, now this fiber is what now? When compared to this fiber, nearer. So when this fiber is nearer, what about shear stress more or bending stress more? Here shear stress I taken tau, but here shear stress should be more. Shear stress what more now? So this value should be what now? Tau 1 is greater than tau y. Tau 1 is greater than tau. But here bending stress. Here bending stress less or more? No, less. But here we cannot see the bending stress magnitude. Always bending stress variation can be seen in a plane perpendicular to plane of cross section. On the cross section they will become as the dots. Here you are getting only direction you are getting. Bending stress magnitude you cannot get it now. They will become as the dot. But this bending stress what now? Sigma b1, that is less than sigma b. This is it is less than sigma b. Now here bending stress 0. But which one is maximum? No, shear stress is maximum. Here you are getting only tau xy. So always in a fiber both bending and shear. And here you are going to get a now this will be tau max. Tau max. Now what this figure is giving now? We are getting the direction you are getting, magnitude you are getting, but we cannot get the variation. Suppose this 20, this is 50, this is 100. We cannot take the linear or parabolic now. So this figure will give the variation, but here we will not get the direction. In all the textbook, they will draw this figure only. Because generally you are entering the variation. But with this one, we cannot decide either tau xy, tau yx or tau xz. We cannot get the direction. So here direction is missing. In this case, which one is missing now? Magnitude you are getting, direction you are getting, but variation you cannot get it. So both are going to be required. Now this will give the direction. From this only we can decide the tau xy, tau xz, tau yz are like this. We can decide it now. But we cannot get the variation. But here we will get the variation. We cannot see the direction. But what about the bending stress? Bending stress will get only direction. Bending stress will get only direction. Bending stress will get only direction. We cannot get the magnitude. We cannot get the magnitude. So here bending stress is going to be maximum. I have assumed as sagging, sorry, hogging. Hogging means above you are going to get a tensile. So this will be maximum, but there is no shear stress. But where you can see the variation of the bending stress in a plane perpendicular to plane of cross section. Bending stress variation can be seen in a plane perpendicular to plane of cross section. The centroid, this is which axis? No, polar axis. Which one the polar axis taken? X. This is VCA and this is HCA or neutral axis. Here bending stress is going to be maximum. Is a perpendicular normal sigma in which direction? X. That's why what you have said, now bending stress always in the direction of the polar axis. So bending stress, now this figure gives the direction or magnitude or both now. Direction you are getting sigma x and variation you are getting magnitude, all are getting now. Direction is what now? In the direction of the x-axis, that the polar axis, perpendicular cross section. Magnitude you are getting, variation you are getting. But what about the shear stress? Here you are getting the direction and magnitude, but variation you are not getting. But here you are getting magnitude and variation, but will not get the direction. Now you can see now overall extreme fiber, here bending stress is there, shear stress 0, means only sigma x, shear stress 0 means uniaxial. And here sigma x is there as well as tau xy is there, tau xy is there. Inner fiber both bending and shear, but at the neutral axis bending stress 0, only shear stress there, pure shear state of stress. So far you have studied the pure shear means sigma x 0, sigma y 0, tau xy equal tau. That is the pure torsion you have studied. But the one more example for pure shear state of stress, that is sigma x 0, sigma y 0 and tau xy equal tau max. What the example now? Any point on the neutral axis of a beam under simple bending. Any point on the neutral axis of a beam. Any point on the neutral axis of a beam under simple bending. Simple bending means what now? Where shear stress is going to be maximum. Now write on this comparison quick. On the cross section, 4 stress you have studied now. 2 shear stress and 2 normal stress. Axial and bending. That comparison you have studied. Axial and bending stress variation. Bending and torsional shear stress you have studied. Axial and bending, torsional shear stress you have studied. And this is about the bending and shear stress. This is always possible in under simple bending. But in the first comparison now, left hand side, bending stress perpendicular to the cross section of the beam. Bending stress is perpendicular to the cross section of beam. Bending stress is perpendicular to the cross section of beam. Within bracket, that is in the direction of the polar axis. That is in the direction of the polar axis. Means bending stress sigma x or sigma y or sigma z, any one, whichever you are assuming the polar axis. In our case, which one you have taken polar axis x. So bending stress becomes sigma x. Somebody is going to assume the polar axis z, then bending stress sigma z. That is in the direction of the polar axis. Right hand side. Shear stress is parallel to the cross section of beam. Shear stress is parallel to the cross section of beam. Shear stress parallel to the cross section of beam. That is in the direction of VCA. That is in the direction of VCA. In the direction of VCA. Why VCA? Because beams are always loaded with a VTSL. By chance HTSL is there. Machine components are loaded by HTSL. When a HTSL is like this, when a shear force like this now, then shear stress will become as about a tau xz. But beams are mostly loaded with a VTSL. That's why I written as about now in the direction of VCA. Next, number 2. Bending stress varies linearly. Bending stress varies linearly. Bending stress varies linearly from fiber to fiber. Bending stress varies linearly from fiber to fiber. Right hand side. Shear stress varies parabolically. Shear stress varies parabolically. Shear stress varies parabolically from fiber to fiber. Shear stress varies parabolically from fiber to fiber. Number 3. Number 3, at extreme fibers, bending stress is maximum. At extreme fibers, bending stress is maximum. Somebody will ask which extreme fiber, top or bottom, in what the answer now? Which are far away from the neutral axis. When centroid is exactly at the mid depth, bending stress maximum both extreme fiber, top and bottom. But in triangular, it is maximum at the top fiber. T section maximum at the bottom fiber. Right hand side. Shear stress is maximum. 1 minute, slightly change it. At extreme fibers, shear stress is 0. At extreme fiber, shear stress is 0. Extreme fiber shear stress is 0. Right hand, next one, left hand side. At neutral axis, bending stress is 0. Right hand side. At neutral axis, shear stress is non-zero. At neutral axis, shear stress is non-zero. Shear stress is non-zero. And becomes maximum at the neutral axis, in case of circular, square, becomes maximum at the neutral axis in case of circular, square, rectangular, I section and T section. Circular, square, rectangular, I section and T section. Which list is missing in that now? Triangular and SD is missing. In triangular and SD, it is not maximum at the neutral axis. Next. At the junction fiber, at the junction of flange and web, left hand side. At the junction of flange and web, only one bending stress value exists. At the junction of flange and web, only one bending stress value exists. Because bending stress proportional to y. At the junction of flange and web, only y is same. Right hand side. At the junction of flange and web, two shear stress values exist. Shear stress inversely proportional to B. Width of the flange and width of the web are different now. Width of the flange is more, width of the web is less now. So since the two different width, two different shear stress will be there now. At the junction of flange and web, two different shear stress values exist. Next, left hand side. Bending stress variation consists of two similar triangles. For any cross section of the beam. Bending stress variation consists of two similar triangles for any cross section of the beam. For any cross section of the beam. Any cross section of the beam. Right hand side. Shape of shear stress variation. Shape of shear stress variation varies from cross. 1 minute. Shape of shear stress variation may vary. Shape of shear stress variation may vary from cross section to cross section. Shape of shear stress variation may vary from cross section to cross section. Next, write down this now. Equations, write down now. What the bending stress in a fiber now? Or what you can write down now? Sigma B max into Y by Y max. And what the sigma B max equation now? M by Z E Y max upon R. And what the shear stress equation now? Three by two for circular, square, rectangular and triangular. But what the triangular differ from these two now? Constant is same. But in square and rectangular, maximum will be at the neutral axis. But in triangular is not maximum at the neutral axis. Constant is same. But location is not same. So close the table. Now write down the regarding the state of stresses now. Write down the state of stresses. Table is comparison is completed now. Next, under pure bending, that is bend moment is constant and shear force is 0. That is bend moment is constant and shear force 0. Right, close. Under pure bending, within the bracket, bend moment is constant, shear force 0, comma. uniaxial state of stress is developed. Uniaxial state of stress is developed at any point on the cross section of the beam. At any point on the cross section of the beam, except at the neutral axis. At the neutral axis, there is no bending stress. Uniaxial state of stress is developed at any point on the neutral axis. At any point on the cross section of beam. At any point on the cross section of beam. That is sigma x is equal to sigma b. Sigma x is equal to sigma b or sigma b max. When you are going to get sigma b max, extreme fiber, sigma x is equal to sigma b or sigma b max, comma, sigma y is equal to tau xy equal to 0. Sigma y is equal to tau xy equal to 0. Hence Morse circle is a circle which is tangential to y-axis. Hence Morse circle is a circle which is tangential to y-axis. Morse circle is a circle which is tangential to y-axis. Next point, under simple bending, that is when both shear force and bendment are acting on the cross section of beam. That is when both shear force and bendment are acting on the cross section of beam. Under simple bending, that is when both shear force and bendment are acting on the cross section of beam. Following state of stress are developed. Following state of stresses are developed. Following state of stress are developed. Number 1. Uniaxial state of stress is developed at any point on the extreme fiber of the beam. Uniaxial state of stress is developed at any point on the extreme fibers of the beam. Extreme fibers of the beam. Extreme fibers of the beam. Within bracket, that is sigma x is equal to sigma b max. Sigma x is equal to sigma b max, comma, sigma y is equal to tau xy equal to 0. Sigma x is equal to sigma b max, comma, sigma y is equal to tau xy 0. Hence Morse circle becomes tangential to y-axis. Tangential to y-axis. Right side or left side depend upon the boat of sagging or hogging. If you take the sagging case, top compressive, in Morse circle the tangential wax on the left side. Hogging, top you are going to get a tensile. Then a Morse circle tangential to y-axis on the left side, right side. Next. Biaxial combined stress are developed. Biaxial combined stress are developed. Biaxial combined stress are developed at any point on the inner fibers of the beam. Biaxial combined stress are developed at any point on the inner fibers of the beam. Inner fibers of the beam. That is sigma x is equal to sigma b. Sigma x is equal to sigma b, comma, sigma y is equal to tau xy, sigma y equal to 0, sigma y is equal to 0, and tau xy equal to tau, tau xy equal to tau. Tau xy equal to tau. Hence, Morse circle is a circle. Morse circle is a circle which is unsymmetric about the origin. Morse circle is a circle which is unsymmetric about the origin. Which is unsymmetric about the origin. Next. Pure shear state of stress. Next point. Pure shear state of stress. Pure shear state of stress is developed at any point on the neutral axis of the beam. Pure shear stress is developed at any point on the neutral axis of the beam. That is sigma x is equal to sigma y is equal to 0. Sigma x is equal to sigma y is equal to 0. Sigma x is equal to sigma y equal to 0. Tau xy is equal to tau max or tau. Tau max is equal to, so tau xy equal to tau max or tau. When it is tau, when it is the tau max now, circular, square, rectangular and I section and T section. But if you go for a triangular and SD, it is not maximum. That's why I written tau. Hence, more circle ಇದೆ. Hence, more circle ಇದೆ. More circle is a circle with the origin of the center. More circle is a circle which is the more circle is a circle with origin of the center. Now with this one, now you can complete the 2 questions are pending on the principal stress chapter. 2 questions are pending on the principal stress chapter that you can complete it now. So that now principal stress chapter is also completed all. Now I am drawing the shear stress variation for triangular. Because remaining all what now? Maximum than neutral axis. But in triangular and SD is not maximum than neutral axis. If anybody want to derive it, same thing you have to do it. But here width is varying. But in rectangular case, width was constant. Most of the objective questions are going to be on the cross that constant values. Other one is variations. 4 variations are given us to identify which is the appropriate variation. maximum will be 50% more than average, but at the neutral axis 33% more. So the maximum shear stress 9 by 8, that is 12.5 times the shear stress at the neutral axis. 12.5 times the shear stress at the neutral axis. But most of the textbook they are mentioning maximum at the neutral axis. Every time is not valid now. Next, SD. Square cross section with diagonals are vertical and horizontal. Square cross section with diagonals are vertical and horizontal. Some students will ask once again, sir, what is the SD? Already I studied bending stress chapter. Square cross section with diagonals are vertical and horizontal. H is about the height of the diagonal. So here it is maximum at a fiber located distance of 3h by 8 from the extreme or h by 8 from neutral axis. In the workbook same question is given now. 4 variations are given us to identify which is the appropriate variation. So it is once again not maximum at the neutral axis. At the neutral axis it is equal to tau average, but here this is 9 by 8. Sometimes side of the square is given, sometimes the diagonals of the square is given. Height of the diagonals is given. So it is maximum at a fiber located distance of h by 8 from neutral axis or 3h by 8 from the extreme fibers. But what about the bending stress? For all the case, you are going to get the two similar triangle. But what about the shear stress variations? That's why what I written, the shape of the shear stress variation may vary from cross section to cross section. For what about the bending stress? Whatever may be the shape of the cross section, bending stress variation consists of two similar triangles. But next is what now? I section and T section. Here junction, two different width, then two different shear stress there. Generally at every fiber you are getting only one shear stress, because fiber to fiber, at every fiber only one width is there. If you take a fiber here, how many widths now? Only one width, one shear stress. But the junction of flange and web, two different widths are there. Then at that time two different shear stress are there because of shear stress inversely proportional to B. This is what now? Width of the flange. So I have taken B1. This is neutral axis. Now this is the width of the web. So I am taking some, if I am taking this B and this B dash, now what about this line now? This line is called as what, the bottom of the flange or top of the web. This line is called as what, the bottom of the flange or top of the web. Then you are going to get the two different shear stress are there. When this line is belongs to bottom of the flange, width is B. When this line is belongs to top of the web, width is what, a B dash. Two different widths are there, two different shear stress. So shear stress at the bottom of the flange is going to be less. Shear stress at the top of the web is more because of what, the width is less. Always extreme fiber is 0. Here is 0. So when I am coming to the neutral axis to bottom, what happens now? Shear stress will increase. Here is 0. When I am coming to the neutral axis to the bottom, what happens? Shear stress will increase. How it is increase now? Parabolically will increase. Increase parabolically. Now here two different widths are there. Here one rectangle, everywhere the width is same, therefore one parabola will be there. Here suddenly width is decreased. When suddenly width is decreased, what now? Stress suddenly increases now. Means you are going to get a horizontal line. Sudden increase is there. Therefore remember what now? Always at the junction of flange and web, two different shear stress inversely proportional to B. Now once again here what, the width is same. So you are going to get a one parabola. Now once again here will increase. increase. Now it is a mirror image. Above and below is the same. Then once again you are going to get the variation is mirror image, you are going to get it now. So this will be the what now? Shear stress at the bottom of the flange. F means what now? Flange. JF mean bottom of the flange. This is top of the web. What should I call this line now? What is this red color line? Bottom of the flange. And what about this blue color line? This is what now? Now if you take any point on this red color points, if you take any point on this red color line, width how much I have to take? No, B I have to take it. But when I am calculating the stress, any point on the blue color line, width which one I have to take it? No, B dash. So here width is going to be less, therefore stress is more. What about these red color points? They are on the bottom of the flange. So when I am calculating the stress here now, when I am calculating the stress at the bottom of the flange, which width I have to take it? No, B. So width is more means stress is less. Similarly, when I am calculating here now, these blue color points on the top of the web, then which width I have to take? No, B dash. So when the width is less, shear stress increases now. So always remember what now? Always a junction fiber. That is about a T section, I section, channel section. Always here what you have studied, T section, I section, they are all what now? Assembly of number of rectangles. T section assembly of 3 rectangles you have studied now. T section is the assembly of 2 rectangles. One junction will be there. T section is about the assembly of 2 rectangles. I section assembly of 3 rectangles. If I keep it like this is what now? Channel section. So always about at the junction you are going to get the 2 different width, 2 different shear stress will be there. Now, there is one question in the workbook now. How to find out the at this red color point, that is what now? What is the meaning of this now? Shear stress at the this called as the junction. When junction fiber in the bottom of the flange. What is the meaning of this now? What should I call this now? Junction fiber. It is a junction of what? At the junction of bottom of the flange and top of the web. J means junction fiber. So what this stress is representing now? When the junction fiber is the bottom of the flange, that is at the red color points. How to find out this stress now? P by I. Now this line is what now? Above the neutral axis or below neutral axis? This red color line is above the neutral. Then I have to take it above area. So if I am calling this is what now? Area of the flange. So I have to take it area of the flange. Next, Y bar. Y bar from where you have to measure it now? y bar of the flange upon which width now? We are calculating the stress at the points on the red color line. So what this width now? BF. Now how to find out the shear stress here now? It is inversely proportional to width. Shear stress inversely proportional to width. BF. So from this one, this is the one calculation. From this one, we'll calculate the stress at the red color points. And from this one, we can find out the blue color points. So if I know the what now, shear stress at the bottom of the flange, we can find out the top of the web. Top of the web we can calculate now. In the workbook, there are two questions are there. This width is given 120, this is given 120, and this is given 20. This is 120 and 20. Mean width is decreased by how many times? Now 6 times. So stress will increase 6 times. And is given stress at the red color points is given. Stress at the red color points is 10. Now what the stress at the blue color point? 60. This width is 120. This width is 20. Stress decrease, width is decreased by how many times now? 6 times. Then stress will increase by what? 6 times. So when the stress at the red color points is 10 megapascal, stress at the blue color point is 60. Now to find out that the neutral axis, this is what a neutral axis. If you want to find out the neutral axis, what you have to do it now? Here I have to calculate it now. At the neutral axis. Then I have to take it above or below, any one. But above how many? Half flange is there, half of the web is there. Then what should I write now? P by I, AY bar of the flange plus AY bar of this half of the web upon this width I have to take it. Similarly, how to find out the shear stress at the neutral axis? P by I. First you have to find out the moment of inertia about neutral axis. So I am calling this a A1 I am calling now. This is Y1 bar I am calling now. So what should I write now? A1 Y1 bar plus this area. This area is A2. And this centroid here now. Y2 bar. So A2 Y2 bar upon this width. What the B you have studied now, where I am calculating here now. So this width is width of the web or width of the flange, width of the web. What the A1 now? Area of the flange. What the A2 now? The area of the web above the neutral axis. This red color is A2. So A1 Y1 bar plus A2 Y2 bar upon this now. So if we want to draw this variation, how many calculations are required now? We have to use this generalized formula 2 times. One is for bottom of the flange, other one is neutral axis. How to find out the top of the web? Top of the web you can calculate by using the ratio of the width. So generally this is for conventional, but in the workbook one question I have given, that is for gate civil engineering question now. But most of the mechanical we are getting that questions only variation or otherwise variations are going to be asked, otherwise based upon the constant. But in the workbook one question is given on this now, asked to find out the shear stress here now. So directly can calculate now. So first you have to find out the moment of inertia about neutral axis. But objective question directly they will give the moment of inertia about the neutral axis. But if you go for a T section, what the last one now? T section, what change you are going to make it now? T section, only one junction is there. One horizontal line will be there. Therefore, always remember what now? Whenever the width will changes, when the width is suddenly decreased, means stress will suddenly increase, means horizontal line goes towards right side. But what about the bending stress variation? Two similar triangles. Here bending stress, only one bending stress will be there because bending stress does not depend upon the width. Bending stress my by I. So here you are going to get only one bending stress. That's why in the comparison I have given now. At the junction fiber only one bending stress, but two different shear stress are going to be there now. Once again, top of the flange to bottom of the flange. Top of the flange to bottom of the flange, one parabola. Now suddenly width is decreased. Suddenly width decrease means sudden increase will be there now. And here tier one parabola. So you are going to get a three parabolas. Top of the flange to bottom of the flange, one parabola. And top of the web to nucleus, one parabola. And nucleus to bottom of the flange, bottom of the web, one parabola. So with this one, now this chapter is completed. Now presented in such a way that all the questions you can do it now. I've already mentioned, but number of questions are till now is very less. Almost gate paper last 15 years, I can tell it only hardly one question is there now. But we cannot predict it. But this is required even about the principal stress chapter. So now complete with this one. Shear stress in the beam questions. All the questions of chapter number 5 you can complete it now. Remaining questions of chapter number 5 and the principal stress chapter, the two questions were pending. Principal stress chapter, two questions were pending. That is question number 20 and question number 38. Chapter number 7, two questions were pending. Question number 20 as well as 38. So with that one, chapter number 7 is also completed. So now pending with only 8, 9, 10. 8, 9, 10. So that you are going to discuss tomorrow. Only these three chapters will take the 7.5 hours. So that you are going to complete it tomorrow. So today's lecture is completed. So complete the deflection of the beam questions. Deflection of the beam questions, you can complete it. Only except two questions. For two questions, you need the principal moment area method is required. Except question number 4 and question number 2. Question number 4 and question number 2. Question number 4 and question number 2. Remaining all the questions, you can complete it now from chapter number 5. Chapter number 5. Sorry. Question number 2 and question number 4 from chapter number 4. Question number 2 and question number 4, except the question number 2 and question number 4 of chapter number 4. Remaining all the questions you can complete based upon the class notes. Most of the questions are done it directly. And chapter number 5 also you can complete it now. And chapter number 7, two questions are given, that also completed. And I've already mentioned tomorrow before attending the class. Tomorrow class, please try to refer the summary table of the theories of failure before coming to the class. So lecture is completed. Thank you one and all for your cooperation. So tomorrow we'll have the last 3 topics, 7. It will take the 3.5 hours for the theories of failure, 1.5 hour for the your columns as well as the thin pressure vessels. And the shear stress regarding opposite.